Last week we have talked about like how to control the roughness for the principal components and how to do the FPCA on multivariate data, right? So we talk about the ideas, and today I will show you some R examples on how to do this in R. So again, we are using the FDA library. So let's first talk about how to do the smooth version of FPCA, where we can control the smoothness of functional principal components. So we were using the Canadian weather data as the examples. So we first created a free basis functions with 365 basis functions. And then we define the harmonic acceleration differential operator. And then we will smooth the temperature data using these basis functions and the harmonic acceleration differential operator as the defined roughness penalty, and the smoothing parameter is equal to 10 to 4. Okay. So we can take a look at how the smooth curve looks like. So this is the smooth function. Okay. So I also tried the different values of the smoothing parameters. For example, if we using set the smoothing parameter to be 10 to minus 2, then we can do the smoothing and see how the smooth looks like. So this will be the smooth temperature curve using lambda equal to 10 to minus 2. You can see it is more rough now, right? Yes. And so if we want to using 10 to 6, as the smoothing parameter. So not surprisingly, when we're using a smoothing parameter as 10 to 6, we'll get a much smoother temperature curve, right? So among these three versions, so this is 10 to minus 2, and this is 10 to 4, right? The middle one is 10 to 4, and this is 10 to 6. So before we doing LPCA, we do this smooth estimation on this temperature. So which one do you think we should use? Any ideas?
Well, last time, like you mentioned that before doing the FPCA, you want to retain as much data as possible.
That's right.
So I guess you take the one that captures as much of the original data as possible.
Yes, this is very good answer. Yes, I agree. So because before we doing LPCA, we want to keep the maximum information from the data. So somehow we will tolerate the roughness on the fitted curve. So therefore, we will using like kind of rough estimation on these curves. So in this case, I will recommend 10 to lambda equal to 10 to minus 2 when we do the LPCA. Okay, so let's see how it looks like. Okay. Sorry. Okay, so so we were using smoothing parameter lambda equal to 10 to minus 2. So we were using these curves to do the LPCA. So these curves are the temp FT2, right? So we are using this to do the LPCA, and so we're still using the function PCA.FD. Okay, so the first one is the kind of the smoothed curve you use, and then the next one will be the number of principal components you want to keep, and also the third argument will be the roughly the penalty on the principal components. So in this case here, I choose lambda to equal to 10 to 6. So this is lambda 10 to 6. Okay, so this is actually 6. So the curve to the FPCA with the roughness penalty on FPCs, we use the curves with the smooth estimated with the smoothing splines with the smoothing parameter lambda equal to 10 to minus 2. Okay. Because the curves are very rough, therefore here we want to put a larger smoothing parameter, 10 to 6, just to make sure the LPCA is smooth enough. You can try different values of the smoothing parameter. So here I just choosing 10 to 6. Okay, this is also explained to you. Like I remember in my previous lectures, when students ask why for the temperature curve, I get 2 different results. So one result is to show the LPC actually pretty smooth. The other one to show the LPC very rough. The reason is how we do the pre-smoothing on the curves. Okay, so you can imagine here, because the curve here is very rough. If we're using a smaller value for the smoothing parameter, the LPC will be very rough as well. Okay, yeah. So here we have a pretty big smoothing parameter on the LPC, 10 to 6. Okay, so I do the LPCA. And I get the principal components, which is called harmonics in the package. And then I evaluate this LPC on this time point 1 to 365, and then I plot these LPCs. Okay, so this is the estimation. So you can see here, because we're using a large smoothing parameters, we are able to obtain the smooth estimation on the LPCs, although the original curve are pretty rough, right? Yes. Okay, so this is kind of give you the ideas on why we need the roughness controls on the LPCs. Any questions? Is this clear? So you can also try different values for the smoothing parameters on the LPC and to see how it looks like. So as we mentioned in our previous lectures, the primary benefit to using LPC is the dimension reduction. You are able to project one infinite curve to a finite space on the LPC scores, right? So this is one major benefit. The other one is that if you get partial observations on other curves, you are able to reconstruct for the whole curve, right? So, so here just show you one examples. So here we first do the LPCA on the temperature curves without the Montreal curves. So just using -12. So this is kind of remove the Montreal temperature curve in the data. Okay, so we still keep 4 LPCs, and we define the harmonic oscillatory differential operator with the smoothing parameter 10 to 6 as the roughness penalty. So we do the estimation, LPCA. And then we get the LPCs and also the mean curve. So now we have the Montreal temperature data, right? So this is the Montreal temperature data. So if I look at the dimension of this Montreal data, this. So this is a delay temperature data for Montreal. So we have this LPC, right? This LPC here. So we evaluate the LPC in the day from 1 to 132, and also we evaluate the mean curve in this first 132 days. We remove the mean curve from the temperature from the Montreal data, because the LPC always working on the center data, right? So then we will so basically here the Montreal curve will be a linear combination of the 4 LPCs, right? So therefore, we just need to do a regression of the Montreal data in the first 132 days with the FPCs, right? And then we will get the FPC scores. So the coefficient of the linear regression will be the LPC scores, right? Yes. So now we get these scores coefficient, and then we can multiply these scores with the LPC and also plus the mean curve. We can predict for the Montreal curve, right? Okay, so now let's plot how the prediction looks like. So here, these black dots are the observed Montreal temperature, and these blue solid lines are the predicted Montreal temperature just using this first 132 days data, okay? And you can see here, the predicted curve actually is pretty close to the observed temperature in Montreal after 132 days, right? Yes. And here, these dashed lines is the mean temperature curve. Okay. Any questions? Is this clear? Okay. Yeah. So you can see FPCA can also help us to do the prediction after we obtain the principal components. Because when you do the LPCA, you're kind of doing the dimension reduction, right? And then when you do the prediction, it will be much easier because you basically know the covariates, and then it's just 4 covariates. So the prediction actually is pretty easy and robust. Okay, so this is a smoothed version of FPCA. So now let's switch to the next topic. Is for the multivariate FPCA. So we are working on the gate data I showed you in our lectures. So basically, this is the data for the angles of hip and knees in degrees in move cycles for 39 boys. Okay. So this is the time for the observations. So we make like 20 equally spaced between 0 to 1, and then we can plot the hip angles data and the knee angles data. So this is for the hip angles data in the whole cycle, and this is the knee angle data for the whole cycle, okay, for 39 boys, okay. We can also do in the phase plot is to plot the hip angles versus the knee angles, and you can see there's a circles in this phase plot. Okay, so now because this gate data is periodic, right? So therefore, we're still using Fourier basis functions. So here we're using 21 Fourier basis functions. Okay, and we also using the harmonic acceleration differential operator, and then we do the smooth splines on the gate data. So the smoothing parameter is set as 10 to minus 11. Again, because this cycle, this gate data is already pretty smooth, right? So therefore, we don't want to put too much smooth roughness penalty on this curve. We want to keep this curve as much as possible. Okay. So then we can plot how the smooth data looks like. Okay. So this is the data. Smooth data looks like. Okay. So let's see. So if we compare to the original data, and you can see, although we're using a very small smoothing parameter, the smoothing spline estimation is already much smoother than original data, right? Yes. Do you know what's the reason for that? Do you know the reason? I guess the reason is because here we only using 21 basis functions, right? So therefore, there's not many basis functions when we bending the these curves. So we can using a smaller small value for the lambda, we can already got a pretty smooth estimation for the curves. Okay. So here we can also look at the correlation on the on this two-dimensional Okay, so this is a image plot. I have to download the using the library fields. So I can look at the correlation coefficients for these two covariates. J. So should be 1, 2, 3. This is the gate. Okay, so this is the correlation coefficients between different time point S and T, or different phase in these gate cycles for the hip versus hip, hip versus knee, and knee versus knee, right? So this is the correlation. So I guess we didn't see much information. I guess the interesting thing to find is that if you look at the correlation between knee and hip in the same time point, like in this diagonal part, right? So the correlation is roughly 0.6. This is 0.6. Okay. Yeah. So there's a strong correlation when the time for the hip and the knee are close enough, right? If it's far away, then the correlation actually becomes very small. It's only 0.2. Yeah, so this is 0, this is 0.2, this is minus 0.2. Actually, this is the negative correlation here. Okay, this is part of the negative correlation. Okay, anyway, so this is how you look at the correlation between the two covariates, two functional covariates. So now we're doing LPCA on these two functional variables at the same time. So so this geta FD is the functional data when we do using the smoothing splines on the hip angles curve and the knee angles curve, right? So then we're doing the LPCA on these two variables at the same time, and then we can first plot the mean curve of these two hip angles and the knee angles. Okay, so this is the average curve. Okay, pretty smooth. And we can also look at the phase plot on these mean curves. So this is the mean cycles. Okay. So then we can also look at the smoothing, the eigenvalues. So remember, the PCA dot values will provide the eigenvalues. So so here, see. So we can plot the eigenvalues. So you can see the eigenvalues decrease very quickly, right? And we look at the accumulated proportion, and you can see here the first 4 principal components will be taking account to 86.7% of the total variations. And then we can plot the FPCs. So this is the simultaneous FPCA on the hip curves and the knee angle curves. Okay. Any questions?